In this tutorial, we will investigate the different models used to describe bonding. There are a number of models that can be used, however, of course, each one of them has some limitations. We will take an example, the molecule CH4, methane. Methane is made up of one carbon atom and 4 hydrogen atoms. Let's start with this 2D ball and stick model. So this is methane. This model shows which atoms are bonded to each other. However, it doesn't show the true shape of the molecule. So this model shows that we have one carbon atom, which is bonded to 4 hydrogen atoms. These are the bonds. However, this isn't the true shape of methane. The angles between the bonds over here are 90 degrees. On the other hand, the 3D formula, so a 3D ball and stick model, shows the true shape of the molecule. So again, we have one carbon atom which is bonded to 4 hydrogen atoms. However, the angle now is different. The angle is about 109.5 degrees. And this means that the true shape of methane is a tetrahedral shape. So notice over here the shape of the tetrahedron. So a 2D ball and stick model will show only the atoms bonded to each other, whereas a 3D ball and stick model will give the true shape of the molecule. We can also use dot and cross diagrams. These diagrams show which atoms the electron in the bonds came from originally. But in reality, you have to pay attention that all electrons are identical. So this is methane, CH4. We have one carbon atom and 4 hydrogen atoms. These are the shared electrons in each bond. The dot represents the electron coming from carbon, and the cross the electron coming from hydrogen. But of course, in reality, all electrons are the same, even though they come from different atoms. However, to differentiate between them and to make representing the bonding between carbon and hydrogen easier, we can use dot and cross diagrams. The circles over here show outer shells. These diagrams show electrons as fixed in positions between the two atoms. However, now we believe that electrons in covalent bonds are constantly moving. But on average, they are found most of the time between the two nuclei of the atoms they are bonding together. And finally, we have this displayed formula which shows the bonds. So it shows the atoms in the molecule and the bonds between them. A single line represents a single covalent bond, and if we have a double covalent bond, we will use 2 lines as shown over here. Actually, in giant structures, the models can never accurately reflect the many millions of atoms or even ions bonded together in the giant lattices. But models are helpful because they can represent a tiny fraction of a structure. So they can indicate the chemical formula of a compound by the simplest ratio of the atoms or ions in models of their giant structures. So for example, if we take sodium chloride, NaCl, sodium chloride has a giant structure. In a ball and stick model of sodium chloride, there will be an equal number of Na plus ions and Cl minus ions, and this means that the formula is NaCl. So for every sodium ion, there will be one chloride ion.